growth and decay. So here we're going to look at how we can use exponential models to look at how we can look at growth and decay in the real world. So let's consider the function q equals e to the power of t. If we derive this with respect to t, we just get e to the power of t. And e to the power of t is q, so dq dt actually equals q. All right, this time, let's replace t with kt. So when we derive this, we get dq dt equals, well, k is a constant, so when we derive e, we get e to the kt multiplied by the derivative of our power, which is k, so we get dq dt. Well, k times e to the kt is q, so we get our rate of change of q equals q times a constant. And another way to say this is that the rate of change is proportional to q itself. So the rate of change of q is proportional to q. And this is going to be the basis we use for our growth and decay model, where k is some constant, and if k is positive, so if k is positive, we have growth, and if k is negative, we have decay. So let's look at an example. So we have the population of rabbits is 1,000 in the year 1995. Then in the year 2000, the population has increased to 3,000. Our first part of our question is we want to show that p equals p0 e to the kt satisfies dp dt equaling kp. That's what we just looked at. Well, let's just double check. So if we find dp dt, we'll get, so we have an exponential. So all we want to do is we get the exponential function itself multiplied by the derivative of our power, which is k, and we get the exponential function itself, and all of this just equals p, so we can see that dp dt satisfies our function equaling kp. So that's true. Next part, we need to find the values of k and p0. So P0 actually always represents our initial population, which we've already been given as 1,000, but let's just double check. So up here, we can say initially t is 0, so t is always 0 at the start, and this is 5 years later, so here t must be equal to 5. So let's first, so we've got our formula, p equals p0 e to the kt. So we know initially the population is 1,000, so let's put in p is 1,000, and initially means t is 0, so anything to the power of 0 is 1, so we just get p0 times 1, so p0 is in fact 1,000, and that is always your initial population. So what about k? So we can use our second bit of information to find k. So we know after 5 years, the population is now 3,000. So that'll mean 3,000 will equal p0, which we know is 1,000 now, equals k times t, which we know is 5, because 5 years is 3,000. So let's divide both sides by 1,000. So we'll get 3 equals e to the 5k. Let's take the ln of both sides. It's always when we have an unknown power, we take the log of both sides. Now, using our log laws, that power comes down to the front. So we get 5k times ln e. ln e is just 1. Divide both sides by 5, and we get ln 3 over 5 as our value for k, or we can write it as a fifth ln 3. So we can actually write our final model for our population as p equals 1,000 e to the k, which is, we now know is a fifth ln 3, all multiplied by t as our final model. Let's have a look at another question. This time, the mass m of a radioactive substance is initially 10 grams. 20 years later, its mass is 9.6 grams. So first we want to find an equation for this. So whenever we're dealing with growth or decay, we know anything is going to be in the form of some variable, so we're going to go with m because they're using m, equals m0, so the initial, e to the kt. And in this case, we're talking about decay because we're talking about something getting smaller, so we can make that k negative. Okay. So what we want to do now is we want to find those values of m0 and k. Well, remember, initially it's 10 grams, and m0 is our initial figure. So in this case, m0 is going to be 10, so we know m is going to be 10e to the minus kt. So let's use our extra information to find k, because we know 20 years later the mass is 9.6 grams. So we know our mass is 9.6, 20 years later, so we're going to sub in t is 20 and m is 9.6. We can divide both sides by 10, so we get 0.96 equals e to the minus 20k. Take the ln of both sides. Using our log laws, that power can come down to the front. We get minus 20k ln e. ln e is 1. Now we can divide both sides by minus 20. So we get ln 0.96 over negative 20. And that's approximately equal to 0.002. So you notice we got a positive value for k because in our initial equation we already accounted for the negative. If we didn't have that negative, this would have given us a negative result. All right, we have a second part of the question. Is saying how long will it take for the mass to be halved? Right, so this means we're after t, because we're saying how long, so we're after time. And for the mass to be halved, we want the mass, was initially 10 grams, so to be halved, it'd have to be 5 grams. So let's put in all that information. So we want the mass to be 5. The initial mass was 10. E to the, well, we found K, it's 0.002, and we're after time. So we can divide both sides by 10. So we get a half equals E to the minus 0.002t. Take the ln of both sides. So we get E to the minus 0.002t. Using our log laws, that power can come down to the front. So we get minus 0.002t times ln E. ln E is 1. Divide both sides by negative 0.002. So ln a half over negative 0.002. And we're going to get t is approximately equal to 346.57 years. And we can round that up to 347 years.